So the objectives in this particular module aren't, this is not a very long module, which you'll probably love as well, compared to the last two. But the objectives are really to understand high-rise structures. Now, this is not every structure. We're particularly focusing on high-rise because there is a big difference with high-rise than there is to others. And the reason it's difficult for surveyors is that you're starting to get beyond your normal, which we call standard operating procedures. So if you went out and worked with a surveying firm at the moment that's used to doing buildings, you know, like a 5-6 story block of units, then there will be procedures they'd go through. And you would have gone through this in construction, setting out the corners, you know, plumbing up between floors, and that's within the scope of actually normal surveying. But once you get to high-rise, and particularly super high-rise, it goes outside the scope of not only the surveying, but also the way you use equipment and the way you calculate precision in that area. So we're going to look at that. We're going to look at the key elements of survey control. That always comes into it. We'll come back to this about what's dynamic and what's static. The key uncertainties in high-rise construction. You'll be thankful to know there is no question here on least squares that you actually have to do yourself. And we're going to, like we did in deformation surveying, talk about geotechnical areas as well. It's becoming more and more common for surveyors to be involved in geotechnical issues. Now, it has been traditionally in mining, a very close relationship between the two, but now it's becoming in other areas as well. Okay, so when we look at structural health monitoring, this is actually a very common term, SHM. It's mandatory. You have no choice anymore with certain size buildings. You actually have to monitor the health of them. Now, this is for occupational health and safety, obviously, but also for costs. So there's an expectation a building would last a certain amount of time before it has to be changed or before there's a certain maintenance regime. So we look at how a building, how it responds to certain pressures. So dynamic deformation, I'll come back to that, with respect to its design. So the design is a critical factor, something you don't influence. And then they look for structural tests after extreme events. So the recent typhoon in China, you might have seen in Hong Kong, major damage to buildings, right? Now, whether that's caused structural damage or not, people would have to check. And most of the stuff we saw was things like scaffolding being blown around, cranes blown off buildings, things of that nature. But certainly in earthquakes, it's a very major part of earthquakes is to check the structure of buildings afterwards. Right? We don't have many earthquakes in Australia, so Western Australia has quite a few. It had an earthquake of 5.6 last week, and it has in the past. It's not on a fault line. It's actually the reason it had an earthquake is because it buckles like this, because there is no fault line. It's the pressure either side, and just where it buckles happens to be near the wheat belt area in southern Western Australia. And then there's a whole bunch of complex and multiple geodetic and geotechnical systems. So what we're interested in are the sensor systems. So the top one there is things like seismographs, which are really quite simple instruments, very common. Anemometers, right? Wind pressure, it's the sort of things that we've discussed before. That on the measuring side, total stations and GPS. You've got to remember the surveying measurements are just part of the picture. So when we get to data acquisition, it's how we acquire it. Now, traditionally, that would be by measurement and then by booking the measurement or downloading it. Now, more commonly, it's by wireless systems, or in a lot of buildings, they actually have built-in fibre optic cable throughout the building. It's not just for the occupants, it's actually to keep the sensors linked together. The reason for fibre optic is it's very fast, so it can handle real-time systems. The data management system, this can be on-site or off-site, right? But they're a fundamental part of buildings. You know, now that they tend to be real-time, the data management tends to be real-time as well, which also meant for legal reasons. If there's a critical failure or potential for critical failure, people need to know it quickly. And the bottom one, structural performance and evaluation, this happens on a periodic element. Now you see FEM analysis. If you remember last week, we talked about finite element methods, right? Which is basically a mathematical method of saying finite elements, in other words, bits and pieces of points. Right? How do they react from a stress? So not all elements in a structure will react the same way. Okay, just defining high-rise itself now, and there's a whole lot of papers and it goes into more detail in the study book, but this is the definition we use throughout this particular module. So if you look from the bottom up, low-rise really goes up to 6 stories, right? And a story is approximately 5 metres. It does change country to country, which is a little strange because I don't quite know why, right? But it can change up to half a metre. What's the definition of the story? So it's quite different. So this is the thing you're used to. Low rise, that's this building. It's 6 floors high, right? So it's a low rise building. Medium, sort of 7 to 12, which you'll see is most residential apartments in a place like Brisbane that are not in the inner city tend to be around that size. High rise, 13 to 30. This could change because this is becoming very common, 13 floors to 30 floors. Then we get to super high rise, which is virtually greater than 30 stories, right? And so you're getting around 200 to 300 metres high. Right? This is pretty high. And then the mega high rise, so we're actually starting to get super mega one day, it's over 400. Now you've got to remember the highest building in the world is 800 metres. So at 800 metres, this is where in this range, you know, the bottom range is at 20 metres. It's 40 times as high as this. It's very high. And you can go up it if you want to, which is if you want to pay. It used to be free, but now it's, I think, $60 to go to the top. So it's one way of making money is to build a tall building and then charge people to get in. So the reason you've got to keep this in concept is if you're using instrumentation, a total station, for example, is that even if you're at the bottom of the building, when we get to super high rise and high rise, we are hundreds of metres away. So it's not a matter of going, well, you know, I can turn an angle and, you know, I'll turn it to 5 seconds, but it's 50 metres away, so therefore that's going to be 1 or 2 millimetres. When you're suddenly turning angles at that sort of distance, it's going to be a big difference. So keep the concept of the distances in your head. Okay, so some of the high rises around the world, if you look on the left there, they're the sort of, well, this I think was about 2 years old, this listing, right? There's 2 things. One is that if you look at it, I mean, obviously the highest one is a lot higher than the next one, so it's got a way to go. I mean, you know, Brisbane did have a proposal at one stage to build the highest building in the world. For probably the only reason was to have the highest building in the world. You know, not many people are doing it now because they realise that as soon as they build one, someone else comes along and wants to build another one. Right? And you don't get any kudos for being the second highest. So the first one's in Dubai in the United Arab Emirates. The second one's in Shanghai, right, in the Middle Kingdom of China. The third one's actually in Mecca. It's the Royal Tower. It's a hotel complex, right? And in Mecca, it looks big because Mecca is actually not that big a place, right? So it stands out. Then Shenzhen, which is in the southern part in the Guangdong province, and Tianjin, which is in the middle part of China, Seoul in South Korea, and then finally we get to New York. And this is I think the One World Trade Center is the replacement for the World Trade Towers, right? Yeah. And the last one is in Guangzhou, which is, those of you not know, but I mean, it's in Guangdong province and used to be called Canton. And that's why this tower is still CTF, is the Canton Trade and Finance Group. So the name's still kept. So this is sort of ranging from 500 plus to 800 plus, right? In Australia, we have tallest building in Australia, not that far from here, Q1 on the Gold Coast, which you can see from most places, right? Which we, at some stage, will have an interview done with the surveying group who did that, so that could be interesting. Sydney Tower, I mean, it's a tourist thing, you know, so you wouldn't say it's a substantive building, it's just a tower. Sky Tower in Brisbane is quite high, right? And you can see it quite a fair way. So that's 98 floors. Here we're well down the range on the world ones, right down to Melbourne's got a couple of big towers that are similar in size and fairly close together. And there are other proposals made for other high-rise. But we'll see later on that when we go up here in metres, that once we get past a certain height, it becomes an issue. So it's not like, oh, I'm not going to work on super high-rise towers. But if you're working on medium high-rise towers, the new type surveying techniques are coming into play. Okay, so just a little bit on the structure, right? You'll hear this terminology if you read any of the papers. There are some recommended readings on the study desk. This triangle is a fairly good representation. So if you take a frame structure, which is like a trellis structure, a wall structure where you put the walls in mostly prefabricated, right, and just drop them on top of each other, and then a kernel structure, which is you have a centre core, and then the things outside it are less important. Between those, you have all these hybrids, right? The current ones that are popular are core and wall, right? So the walls don't have as much importance. If you want to see a correlative to that, just maybe look at pole houses in Queensland, you know, up around Sunshine Coast on the hinterland, Maleny, that area. You'll see a lot of people with pole houses. Now, mostly those pole houses, the poles take all the stress and strain, and actually the floors and the walls are variable. So if you went to your house, you know, the number of houses you own, and you knocked out a wall, it would not be a good thing, right? The house would probably fall down. You go to a pole house, you just take a wall out. It's not a supporting structure, generally speaking. The second part we want to look at is that the structure also, the type of structure is a guide to the impact of forces. So in this simple case, obviously a building that has no flow through, right? The same amount of wind on that as it would be on a microwave tower, for example, or a mobile phone transmitting tower. The impact of the wind would be less. You know, if you go back to your basic physics, there's an equal and opposite force, right? But that equal and opposite force depends on the surface area, and wind is a particulate. So here you've got 1 million particles hitting that surface, so you have X number of particles per square inch or square centimetre on that surface, whereas on this surface here, you would have the same pressure, but the surface is less. So the total pressure on the structure is less. Okay, so all buildings are relatively simple, and you'll see in the module we've kept to a simple building design, probably because I couldn't draw a more complex one, that was the reason. But you've got to think about this carefully because surveyors are getting more and more involved in tall structures, right? And it's how you start at the base. So this is a core and wall structure, so there's corner columns, but a centre core. And what we're looking at is to say, okay, the things you want is that the columns must be vertical, right? The floors should be horizontal, and the distance between the floors should be the same. I mean, it is that simple. So that's the basic equation. How you do that is the difficult bit. Now, you can say the floor rotates, but the reality is even a floor rotating a bit doesn't affect the structure as much as if it's tilted. Okay, when we talk about most structures, we have structural engineers, which you may or may not have met. They sometimes come out in public. And their major job is actually the twofold is the design, which will be done usually in conjunction with an architect, right? And then materials. Now, we have a diagram I haven't shown you here, but you'll see in the study book there's a diagram showing building types, where they are for high-rise, and the materials. Now, the materials, if you go back 100 years, basically, right, nearly all high-rise past a certain size were steel. So if you see old movies like Alfred Hitchcock movies, that's where you see the movies, or even Abbott and Costello, the comedy movies, you'll see them walking on steel. Steel was the strongest structure, and that was the one that actually you used for the framework of the building. So the Empire State Building, for example, is primarily steel and then clad. Now, nearly all buildings, the majority, are actually concrete, cement, and composite mix. So they've changed in the way they're mixed. And also, by far, the majority of very tall buildings in the world are in either Eastern or Western Asia. There's less being built in what we call the Western Hemisphere. So there's also a location change. And, of course, they're getting taller and taller. The Empire State Building used to look quite incredible, right? But if you go to New York now, it does look a little bit like it's stuck in the middle. The second part is that you've got to be able to tell what natural forces are going to be on it, on the building itself, the structure. Now, that requires a fair amount of research, because not only you can get prevailing winds, temperature changes, frequency of natural events. So in the United States last week with the typhoon, the Carolinas they call it, the North and South Carolina and Florida are often hit by typhoons. So any tall structure there would have to take an assumption that there is a 1 in X number of years typhoon likelihood, and then the category of the typhoon. So in Australia, we have cyclone ratings, exactly the same thing for buildings. They're exaggerated when we talk about high rise because it has a bigger impact. Obviously, earthquakes are well documented, but you can't tell when they're going to happen. That's the biggest issue. And then construction-related activities. This is the one where, as students, you don't think about, but if you're working in real construction, construction causes its own problems. When you stick a crane on one side of the building, it makes the building lean. You put a load on the crane, and it moves more. So there are a whole lot of other aspects you have to consider when you're looking at actually the construction side that cause deformation in the building. There are other things that concrete shrinkage, if you pour concrete, it actually does shrink, yes. You've all poured concrete somewhere, and it shouldn't shrink too much if you've got the right formula, right? And there's a few other factors we'll discuss later on. Okay, just as we said in metrology, as we said in deformation last week, we talked about degrees of freedom. We're not talking about degrees of freedom here, but it's exactly the same thing. So any structure has these 6 degrees of freedom, right? So you have, once again, rotation. You have a screwing or a skewing of the building, right? You have gravity, which is a force downwards. It's constant. Okay, so it's a different type of force. You have movements in X, Y, and Z. And you also have harmonic movements that impact on all those things. Now, harmonic movements are movements that change over time, and they have a certain cycle. So in the harmonic movement here, there's a wavelength and a frequency. And they're well known in buildings. There's a number of buildings in the world. There's one in Hong Kong that people stand outside of because it sings. It actually makes a noise from its harmonics. A lot of buildings in Japan where they use dampening systems, they use reverse harmonics. So they work out the building's harmonics and they work out what an earthquake harmonic would be. And the dampening is actually to cancel out the 2 harmonics. Right? If a big earthquake doesn't normally work. So they're the things that some of these are under your control. X, Y, and Z is particularly under your control. Because there's no use knowing what the forces are if you can't measure what the forces are. That's the role of the surveyor. So the dynamic effects are more critical during construction. The static effects, for example, gravity, long-term earth tides, slow earth movement, tectonic plate like we have in Australia, these types of static events don't really affect you during the construction phase. The dynamic effects do. I mean, if you went on any construction site this morning, the temperature in the morning, 6:30 when people start, is going to be different all throughout the day. The air pressure will change, the humidity will change, the wind will change. Right? And wind is a big factor. So that's the sort of diagram you've got to keep in your head when you're considering any sort of set out or control work. So the types of movements, and in the study book you'll see there's a big table of this, and it's worthwhile looking at the table. Not because it's going to be on the exam. It's just that it's very hard to find in this game a table that summarises these effects. If you look onto civil engineering or structural engineering sites, they'll focus in on one thing. Whereas here you can see the lot in a slightly condensed format. So long period movement, so raft deformation, and I think there's an image. We go back to the couple of slides back. This foundation on the bottom is often called the raft. Right? When you think about the building sitting on it. Now, the concept of a raft is that you spread the building weight across a bigger area. So if you were going to, you think about if you're going to build something at home like a sawhorse, right? You spread the base at the bottom so the weight on the top doesn't shift the bottom, right? In some cases, these rafts are actually floating because you can't get it deep enough to actually go to, say, bedrock or whatever, right? Well, they'll make the raft float on purpose, and then you have to monitor what the movement would be. They're very large and big buildings, massive, and a huge amount of concrete, obviously. So that's the long-term effect. You have concrete creep, which I said before, concrete shrinkage. Then the long-term effect, concrete can actually creep. It can change its shape, right? The recent disaster in Italy, you know, it seems to be that's what they're focused on. What's happened to the concrete that was encasing the columns in that bridge? You know, did it just deteriorate? Did it move? Right? So concrete creep is a real issue. The building design can be such that it actually affects the long-term effect, right? I mean, that's a factor that's outside your control, but you may be involved with monitoring it. The diurnal movements, you should know now that diurnal means the daily movements, right? There's quite a few of them. The biggest one is sun. Now, when the sun on the building here, which is coming up in the east, to my right, when it rises in the morning, that side of the building heats up. This side of the building remains cool. It's still warming up with the air, but not to the same effect. This is a sixth floor building. The impact is relatively small, right? But to give you some idea, the Burj Khalifa, the tallest building in the world in Dubai, it has, in the morning sun on a normal day, it has a 25 millimeter per hour change in height, just due to the sun on the side of the building. And it's been designed to account for it, so other buildings are worse than that, right? Now, steel towers, we saw some before. Steel towers are a thing that people look at and go, oh, it's just a tall tower. But because it's steel, and the expansion rate of steel is greater than concrete, and greater than timber, and other factors, right? Steel towers can move a lot with the sun on them, right? So instead of actually allowing for what they try to do is make sure that all is heating up at the same time. Therefore, the movement is directly up or directly down as it cools. Right, the raft itself at the bottom is any deformation in the raft tends to be in the middle, that's where most of the weight is. The other diurnal effect is that earth tides, you would have done in, I think, Geodetic B or something, the earth moves in and out daily, right? Now, on a very tall building, the effect of earth tide could have an impact. It's usually overridden by other impacts. And the last one, which we are interested in, is dynamic movements. Now, here we define as things that can happen in 10 to 15 minutes. It's not really defined the same way in every single jurisdiction. So, short-term impacts. So, like I said before, wind, cranes, construction effects, solar effect could be short-term. If you think the Burj Khalifa is basically in the middle of a desert, and if you've ever worked in the desert, is one of the things about deserts are they are very, very hot and they're very, very cold. If you go to the Sahara or any of the southern African deserts, you're talking about minus degrees before 7 o'clock in the morning and sometimes 35 to 40 degrees during the day. So the change is dramatic. So you can see here that actually it could be considered a dynamic effect because the change could be rather rapid. As soon as the sun hits it, it changes quickly. Precipitation, that's a big word for rain, right? Which we have a lot of. Snow we don't have a lot of, but that's why you see chalets with steep roofs, right? Because they cause deformation if you've got a flat roof. In Australia, for example, because we look at cyclones, we tend to have gone to strengthening the building. In the past, it was to let air through, to change the pressure. So whichever way the wind was blowing, you would open the windows on the opposite side to remove the pressure from inside the house, because that's what used to blow the roof off. Now we tend to actually just tie the roof down a bit better. Okay, so there's an entire table in the study book that's worthwhile flicking through because it explains it better. One point there that you should remember is when we talk about wind, if you went to the top of the 6th floor here and at the Vice Chancellor's private balcony or whatever is there, you probably wouldn't notice the difference between the wind in the car park and the wind up there, right? But when we're talking about super high rise, it's significantly different. So when you get into a jet airliner, you know when they've got a tailwind, they're talking about a tailwind of maybe 150 miles an hour, right? With the height, the wind changes dramatically. And it's a whole change in eddying. So for city situations, urban situations, if you go to a very large city, actually Brisbane's large enough, is you'll see that people go into the city and it's quite warm from the suburbs, and it's actually quite cool in the city because A, you've got less sun, but you've also got wind swirling amongst the buildings. That swirling wind tends to vortex upwards. So you get one tall building. It not only has the wind pressure from the normal wind, like a southeasterly blowing at 15 knots, it also has this vortex effect coming off the city itself, right? And the city generates heat. There's something to consider. Now, these are some of the displacements. So axial shortening, right, which is engineers use very long words, so that we can all get confused. It just means that the more weight you put on something, the shorter it gets because it starts to compress. So this is some idea of, due to elastic strains this is, right? So we're starting in, this is in millimetres, and that's in stories. So when you get to 60 floors, you're talking about 125 millimetres of axial shortening. In other words, when you build that building, you've got to take into account it's going to get squatter as it goes, right? You know, it naturally sinks. And that, of course, is for one thing. You can imagine it depends on the materials, depends if it's a core wall, perimeter, steel construction, all sorts of issues there. This one's actually off the, I think the Khalifa. I'm not sure. Yeah, it is. That's the design. And this is actually real-time monitoring of the changes. So it's hard to see on this axis, right? But it's the change in X and Y for these particular sensors. Over, it's static changes, but it's going to be monitored 24 hours a day, I guess, for the life of the building. As to the design, it's a triaxial design, which takes into account, it's actually a very clever design. The movement of the Khalifa building in terms of wind, you know, the sway, which is very small. I mean, there's buildings in the US that are, you know, less than a third that size that sway more than that. So their design's a very clever design. And you can see here, they're the wings, and this is a plot of the movement. And if you look on the bottom, you can see there is outliers here, right, which presumably are some major impact, like strong winds or something of that nature. Okay, now the reason verticality is critical, this should be really simple, but it's something you've got to consider. If case A, the whole idea is that if you imagine you put blocks together, right? If the blocks are correctly made and you put one on top of the other exactly, right, then it will be vertical and it won't fall over. Now in case B, which is probably more realistic, if there's small random errors in both the construction and in, say, the surveying, but they are truly random. So in other words, you put up one floor and it's slightly out, it's just as likely the next floor is going to come back this way. So that still will work, right? Won't be as strong because there's a change in the axial correctness of it, but it won't fall over. The real worry, and this is also to do with surveying, is that when you've got a systematic error, so you make the blocks, but at the top of every block is just slightly cut off at one angle. So when you keep on adding it, it'll systematically go up, and then that's what happens. Now, if you look at, well, you guys are probably a bit too old to have done Lego, surely, right? But Jenga, you know Jenga, the game, right? You've played that? Okay. Same principle involved with Jenga. You probably don't notice because you normally play Jenga on a table, right? But if you get clever, and we did this ourselves, we made adult Jenga. So ours is this high, made out of 2x4 timber. And then you really see the impact. So If you're off centre, that's what happens in Jenga. It's exactly the same for a building. So this is why verticality is absolutely a critical thing. And it's something that's difficult for surveyors to be working in other fields, because you normally concentrate your surveying on horizontal angle precision, distance precision, and mostly the vertical bit you worry about from the point on the ground to the instrument. And you think, oh, I've got to be right over the point, you know? Or you worry about a vertical angle to determine height, but actual verticality is not something that you use a lot. Okay, some of the reasons, if you take the normal surveying model, and you'll notice in this talk we always talk about measurement models, that's the surveying model. The reason it can be different in high-rise is that the construction period is quite long. You know, Q1 on the Gold Coast, I'm not sure how long it took, but, you know, it would have taken significant time before you even saw the building start to rise. But the surveyors were involved well before that, you know, a long time before that. So the period of time means that you actually, you have time to maybe establish more control, but it also means whatever you do, a little bit like we're talking about deformation, it could be years, or it could be used later on as monitoring the building. So you've got to consider that right from the beginning. The construction environment, saying it's very dynamic and crowded is sort of an understatement. It's difficult, right? So you have the things that you think from the outside, a person looks at it and thinks, it's always fascinating to watch high-rise being constructed. You have cranes everywhere, you have people running around. You know, occasionally you see a surveyor. These days you can't tell the difference because no one wears different colour hard hats. They used to. You used to be able to define whether you're an engineer, surveyor, or site foreman or something by your hard hat, right? Now we have all the same. But you see a lot of that action. As surveyors, what you've got to look at and go, how does that impact your survey? Some of that is actually, as we've been stressing last time, is invisible. Refraction. Middle of the city, swirling winds, heat, right? The heat tends to rise vertically up because it doesn't get blown away because there's not enough open space, right? And then from a surveying point is that you start talking about very, very steep vertical angles. Things that are very complex that most surveyors are not used to doing. So the ground control is usually very constrained. Just put yourself in any city environment and say you're going to build a 40-story building, right? Where are you going to put the ground control? You know, you've got to be able to see the building. It quickly disappears as well, and it's also obstructed by things like cranes and by cladding. You know, they put cladding up fairly quickly, or scaffolding. You know, the scaffolders actually don't sort of say, oh, I'll put it here so the surveyor can see through. They're not that friendly, right? So you've got to think about those lines of sight, and usually the solution is massive redundancy. Assume you're going to be blocked, right? So you've got to have more redundancy. Now, in some cases, people put control in other buildings. Good idea, if the building's not too high and not subject to movement. No use having your control moving if you're trying to measure other things. And there is another aspect to that. Of course, you have to have permission to do that for access to the building as well as build whatever you want to build on top of it. So that's the security issue on the bottom of that question. So you will know from modules 1 and 2 and other work you've done in the course that observational uncertainties change over height and time, right? So particularly we're interested in height at this particular point. Now most surveyors are not used to very steep angles. So they tend to be able to go, you know, I'm reading at 10 degrees, that's steep. You know? We're talking about sometimes an elevation of 80 degrees. Now, you need to understand this very clearly. If you go back to module 2, I think it is, module 1, there's a section in there that actually contradicts most textbooks about errors in height. And that's because most textbooks are related to set out and using theodolites and older-fashioned measuring equipment. So you have to consider if you're using a total station and you're measuring heights, there is a different scenario, right? So make sure you understand that part of module 1 about vertical angles or zenith distances. It is a different approach. Okay, so obviously as it gets higher, the difficulties of maintaining verticality in X and Y, right, and vertical distances, which is really the Z, all increase, but the design thresholds still remain the same. So it's a little bit an oddity in a sense. that as you get further away from the action, right, your survey becomes less precise, but the engineering design is exactly the same. So on floor 28 or 56, they're going to say the pillars on the four corners have to be set out, or the steel work has to be set out to a certain precision, a tolerance, right, which will be the same as the first floor. But you know, getting further away, that your tolerance or your precision, standard deviation or whatever, is going to change because of the distance you are away from your control. And like nearly everything in surveying, probably in life as well, redundancy is the big issue, right? If you actually put control in and you think this should be enough, just double it. That's probably a good figure to start with, right? You are going to lose control. It might be sight lines, it might be crane dropping, 10 tonne of concrete onto the position you had before, which if you want a new total station, that's a good idea, just leave it there, right? Get the insurance. But redundancy in measurement is the same way. Now you should have seen now as you've done more and more least squares, that least squares thrives on redundancy. Without redundancy, least squares is just a mathematical formula, simple, right? The more redundancy you have in least squares, the better it is. Mind you, in the last assignment where some people said you should be reading the angles 18 times, that probably was going a little bit too far. It's a bit too much redundancy. Okay, we're just going to go through this slide and then we'll have a break. So the principles of precision surveying, which theoretically should be coming into you in this whole program we're doing now, this whole course, right? We didn't call it precision surveying, we called it advanced because it covers a whole lot of topics. But there's a thread of precision surveying through many of the areas. Maximum redundancy in your control. Now, surveyors are used to maybe redundancy in X and Y. They're less used to redundancy in height. They're used to it on the ground because we have a lot of PSMs. If you walked around this campus, you'll find we've got more PSMs with accurate height data on it than we have PSMs with, GDA 94 coordinates, for example. Because people don't want to level a long way. And it was easy to establish those over the years. Most of them were established in the 60s and 70s, and they're still there. Optical geometry. Now, that should be showing, optimal, I should say, geometry. You should be able to see already from the work you've been doing that if you have poor geometry, then either you have to increase your precision dramatically, way beyond sometimes your equipment is capable of, right? The whole idea is to give yourself a good chance to start with. And optimal geometry is critical. Now, when we have our simple views of a building as being square, but you saw with the Burj Khalifa, and you'll see with the Cigar Tower in London, and the Twin Towers in Kuala Lumpur, where they made the movie. Beautiful towers, those. That they're not simple boxes. So your control mechanisms have to really take that into account. So you've got to have a capability of actually not only regularly checking, right, but rigorously checking. Now, as we said in deformation last week, some of those principles you take out of deformation, as we said in metrology, you took some principles out of metrology into deformation. Some of the principles of deformation you need to take into here. So recovery marks, for example, should be such that they're far enough away that they don't get damaged if the main mark is damaged, right? But close enough to be able to recover to a high level of precision. It's a lot easier to put a recovery mark, re-establish a control mark, and then check it, right, from recovery, than it is to go and actually rerun an entire network adjustment because you lost one control point. So it's an area that surveyors tend to think on the side is, I'll throw a couple of recovery marks in. It's something you should think about a little more seriously. It saves a lot of time and money in the long run. And the construction of control for long-term stability and usefulness. I had a discussion last week with someone who said, well, we don't use pillars anymore because they move. If you've got a pillar this high, the ground moves, the top moves more, right? But if you look at, I think it's in the annex of deformation, you'll see some of the construction models for pillars. And I think it was the Western Australian model that it's used quite often around the world, but their design for it is quite clever. So the centre part of the pillar is free of movement of the concrete around it. It's actually an ideal one for high-rise construction and things where there's a lot of vibration, because concrete reacts to vibration sonically and from earth movement, which can actually shift then, right? Whereas if you keep the centre mark of it out of that vibration, and that's why if in doubt, ground marks with a concrete collar are sometimes preferred, because people can drive over them as well without hitting a pole, which helps. Now, accessibility, this, in most cases for surveying, this is not a big issue. On a high-rise site, it's absolutely critical. You'll have few options on site to where you put the survey points. Most developers, civil engineers, structural engineers will know the criticality of the survey. Without that, they can't do a lot, right? So you have a little bit of an edge there, but you've got to get in there early. So where they site the crane base, for example, they won't want to move that, right? But conversely, working inside the crane base is not such a silly thing. They're usually pretty big, right? And you're not going to get hit by anything because they protect the crane base very well. So there's lots of options, but it's something that's got to be thought about early on in the time. And the optimised lines of sight, once again, we talked last week about minimising refraction and haze. For example, if there's a very large genset or a number of gensets on the site, which will be not unusual, right? Then don't make one of your principal sight lines over the top of the genset. Right? It won't be one run by solar panels. It'll be a diesel genset that's noisy and belching smoke and huge gradients of temperature coming off it. Okay, we'll come back to the control network. We're just going to take a break.